We're going to continue the discussion today about the definition of continuity as it refers to a function or the graph of a function. And we introduced the term one-sided limit in the last lesson, or the first part of this lesson, and we're going to continue on looking at that definition of continuity today in a good amount of detail, and using it in different contexts today. And then at the end, we're going to introduce a theorem that has to do with something a property that all continuous functions have. I'm probably going to break this up into about 2 or 3 videos, and so it'll be in slightly smaller chunks for you. But let's go ahead and get started. So let's just review the definition of what it means for a function to be continuous. Now, in just plain terms, we understood that a function's graph is continuous if you can draw all of it on a particular interval without lifting your pen. But let's in particular focus on individual points like this one right here, and I'm going to mark this x-axis as the number c. So let's see what it really means for this function to be continuous exactly at this point. What that would mean is, as I draw the graph and pass through that x value, what is it? Why is it that I can actually do that? And I call this the continuity checklist. So what has to happen first is the function evaluated, the exact value of the function must be defined. So in other words, in a situation like this, it would not be defined if we had something like a hole here. Okay, so in this graph, f of c is not defined, and that's what's causing it to not be continuous, because we have to jump over this hole to keep drawing. Okay, the second requirement is the limit as x approaches c must exist. Okay, so I could draw a graph that has a value of the function but no limit, and then it still would not be continuous. See, so watch, I will draw it again. I'll mark C, and I'll draw my graph, but this time I may even have a defined point, but unfortunately no limit, because maybe I'll come from the other side and approach a different point, right? So this time I have the value of the function, so I could actually check the first item in my checklist, but I cannot check the second one because coming from the left and coming from the right, we're approaching different points or different values. Now, the third situation is I might have a limit, I might have a value of the function, but I still might not be continuous because I could look like this. So let's draw one more. I'll mark my C, and this time I'll draw my graph so that it has a limit and it has a value f of c, which is this point, but unfortunately this graph is still not continuous at x equals c because of the fact this dot did not plug the hole. So the third criterion is, not only do I have a value of the function, not only does the graph have a limit, but those two values had better be the same. So in order for this to work, this dot would have to be moved to be where this hole is. And now, at exactly right there, this graph is continuous because the point that I'm approaching from either side is in fact a point on the graph. Okay, so we're going to investigate this now by showing you a couple of examples where the function is defined in different parts, and we want to determine, is this function continuous? When it says at the given value of x, we're assuming it means at the place where the rule in place for the different parts of the function is changing. And this one, the important number is 4. Okay, so to lay out what we're investigating, the part that I do know is that when x equals 4, the function value is 10. So there is a defined point for 10. So in order for this to be continuous, the graph drawn by the rest of this function must approach this point and leave it as well from either side. And so this says the function is y equals x squared plus 1 as long as x is not 4. Okay, so to draw a little bit of the graph, I might start a little bit over here, like at -1, and draw the first couple points. Like if x is -1, the y value would be 2. Okay, it'd be 2. If the x value were 0, the y value would be 1. And if x is 1, it would be 2 again. So we see it is going to come around. And maybe it is going to head up to here, but we're not quite sure yet. So what we're going to do now is see, as we continue to draw and draw, what is this value going to be approaching? So let's take a look at the limit as x approaches 4 of the expression x squared plus 1. And what we're going to find out is this is a limit that I can get an answer just by plugging in 4. But I do get 4 squared plus 1, which is 17. So what really I'm going to observe is by the time I get to 4, this graph is going to overshoot this point by quite a bit. In fact, I don't even have enough room to draw it. It's actually going to be approaching the point 417, but the graph will have a hole in it as it continues up because it's only drawing this rule whenever the x value is not 4. When it gets to exactly 4, the value drops down to 10. But then once we get past 4 again, it'll just continue on this parabola some more. Okay? So remembering the definition of continuity, the value of the function f of 4 was 10, but since the limit when x approaches 4 was 17, and since those are different, this is not continuous at x equals 4. Now, just so we know, it is continuous everywhere else. So, for example, if I asked about if this were examined at x equals 1, the graph is perfectly continuous through there. The only place that's not continuous is going to be at 4. Okay, I have one more to look at like this. And this one is defined in 3 pieces. And so what that means is when we go to check the limits as x approaches 2, we're going to have to investigate it separately from the 2 sides. So remembering my checklist, we're trying to determine if the function's continuous at x equals 2. So is f continuous at x equals 2? That's the thing to be determined. And so the 3 parts of the checklist are, do I know f of 2? And I look over here at my definition, and it says explicitly when x equals 2, the function equals 2. So yes, I do. I know f of 2, and it's 2. The second part of the definition is I need to look at the limit as x approaches 2. But now, since this time there is a different expression when x is less than 2 than there is when x is bigger than 2, we need to examine this limit in parts, which means we'll take a look at the limit approaching 2 from the left, and we'll take a look at the limit approaching 2 from the right. Now notice when I'm coming from the left, that would imply that x is less than 2, so I'm really using this rule here. I'm really using 3x minus 4 for that part. And if x is approaching 2 from the right, that would imply that x is greater than 2, and I have to use the second rule, 6 minus 2x. And I'm going to examine these limits now, and both of these are limits I can get just by plugging in 2. So I'm going to be able to get 6 minus 4 for this one, which is 2. This one I get 6 minus 4 also, a little bit different way, but it's also 6 minus 4, which gives me 2. And that's a good thing. Now I've got the limit from the right and the left, both equal to 2, which is also what the function equals. And so that's telling me that the point that the graph contains, which is the point 2, 2, because that's the one point we knew, but this one says coming from the left, where we had y equals 3x minus 4, that's a slope, that's a line where the slope is about 3, so I'm going to draw it about like this, okay? And then y equals 6 minus 2x, which is a line with a negative 2 slope, and it's going to be coming off of there, something like this. And they both meet at the point 2, 2. And so this function is continuous. F is continuous at x equals 2. We're going to stop the video here and we'll start a new one where we're going to examine using the definition in a little different way. So stay tuned.